All right, so welcome back to Math 383 Complex Analysis. This is lecture 26. And what we're going to do today is we're going to continue our proof of Fejers's theorem, talk a little bit about Dirichlet's theorem. And the motivation for all of this is to get to Poisson summation. And there are three different ways of defining the Fourier transform. One of the reasons I like the definition I give is it makes Poisson summation particularly nice. And you could do an entire course on Fourier analysis, an entire course on applications of the Fourier transform. We are just scratching the surface. If there's a little bit of time at the end of today, I might talk a little bit about applications of Fourier analysis and the Fourier transform to solving differential equations. Because I noticed some people had perked up a little bit at that, but hadn't really seen all the details. So again, the general items, as always, is the power of smoothness. The more nice properties I assume about your function, not surprisingly, the more you are able to prove. And so in particular, the more differentiable your function is, the better results you're going to get, the better convergence you're going to get. And we saw one of the statements about the Fourier transform that if you integrate by parts, if you are k times differentiable, the nth Fourier coefficient is decaying y 1 over n to the k. So the more differentiable you are, the better you are going to be in terms of having sums converge. We will do a 3 epsilon argument at some point today. How many people have done a 3 epsilon argument in real analysis? If you don't like doing a 3 epsilon argument, you just use epsilon over 3, and then it becomes an epsilon argument at the end of the day. So as you get older, it doesn't really have to equal something strictly less than epsilon. Any universal constant times epsilon is fine, because you can always then just let epsilon equal epsilon prime over whatever, and then it all works out nicely. And then, as always, there is the benefit of detouring into the complex plane, that when we move into the complex plane, we have all of our tools available. And in particular, we might get a little bit into, again, evaluating Fourier transforms by using techniques from complex analysis, which is not surprising because the Fourier transform is the integral against a complex exponential. And one of my favorite ways to evaluate these is to use accumulation points. So that if you're going to evaluate it at a real argument, you then get it for free at the complex argument. Absolutely beautiful trick. All right, so just as a quick recap from last time, we talked about approximations to the identity. So if you want to think of it as a probability distribution, and what you do is you put in maybe some kind of parameter. We did, P was a distribution, we looked at Pn of x was P of nx times n. So as n goes to infinity, you're squishing the mass tighter and tighter and tighter about the origin. Essentially, we're looking at a function where all the mass is at the origin. It's a unit point mass. If you want to think about its density is 0, except at the origin where it's plus infinity, and then goes back to being 0 afterwards, but in such a way that it integrates to 1. There's lots of different ways you can come up with approximations to the identity. You can do a triangle function, which is continuous. You could do a rectangle function, which then has 2 points of discontinuity. You can do a Gaussian. Lots of different ways that you can do it. We talked about the Dirichlet kernels and the Fejer kernels and how these are related to Fourier series. And it turns out that they have extremely nice explicit formulas for the sums. And this comes from just using the fact that we have a geometric series with a ratio. Okay. So the first, as a nice exercise, is that the Fejer kernels form an approximation to the identity. So when we look at the formula as sine squared over n times sine squared, it's clear that it's non-negative. If you look at it, I can write it as e0 of x plus n minus 1 over n, e negative 1x plus e to the 1x, and so on and so on and so on. And this is just going through and looking at what is the Dirichlet kernel, and we're summing these, and goes from 0 to n minus 1. So the e0 term occurs in all big N choices. The e1 and the e minus 1 occur in everything but the 0th term. So that's why you have an n minus 1 over n, and so on and so on and so on. Well, if I integrate from 0 to 1, only the term e0 of x, remember, e n of x is e to the 2 pi I n x. Only e0x integrates to 1. Everything else integrates to 0. So looking at this expansion for fn of x, it's clear that it integrates to 1. It's clear that it's non-negative. All we have to do is show that the mass is concentrated near the origin. So how would we do that? Well, if you look at what's going on, we have an n in the denominator. So as long as the sine squared of pi x is not too small, the n in the denominator is going to be huge, and it's going to make this very, very small. So near x equals 0, fn of x looks like, so what does sine squared of n pi x look like when x is small? So how would you approximate sine of u if u is small? I'm sorry?
I would say 10 squared pi x.
And yeah, so, because it's just going to be, n pi x squared for the numerator, and then the denominator would be n pi x squared. So this is approximately 1 over n when x is small. Did I make a mistake? Oh, sorry, it's approximately n. Sorry, other way around. It's approximately n when x is small. Now, what do we mean by x is small? I want the argument of sine squared n pi x to be close to 0. So x really shouldn't be much more than 1 over n. So think, say absolute value of x, less than or equal to 1 over n as a reasonable scale to try something like this. Okay. You might want it even smaller than that, but on a scale something like that, if it's really, really small, I need n pi x to be a small number. Even if x was of size 1 over n, that's not a great approximation. It's not horrible, but the smaller n pi x is, the better this is. And so what we're seeing is near x equals 0, the function looks quite large. Well, this is essentially no shit. It integrates to 1. Right? It gets really small as we get away from x equals 0. So it should be very large near x equals 0. And we just have to show, when we look at sine squared pi of x, well, the only danger for that is when this is 0. So when is sine of pi of x 0? I'm sorry? When x equals 0. When x equals 1/2, it's actually its largest value. So the only problem is when x is near 0. As we get away from x equals 0, then the sine squared pi of x is going to be bounded from below, and this function is going to be nice. Okay, so you can put in the details and show that this really is an approximation to the identity. All right, so now what we want to do is we want to prove Fejers's theorem, that if we have a continuous periodic function in 0, 1, then given any epsilon, there is an n naught, such that as long as n is greater than n naught, my Fejer approximation is within epsilon of my function. And what's great is this is uniform. I only have to choose an n naught. It doesn't depend on the point x, it just depends on the point epsilon. Okay? And so what we want to do is we want to have some preliminaries first. So let's look at the integral from -1/2 to 1/2 of f of x tn. Let's do f of t tn of x minus t dt. So what am I looking at? This is the convolution. So this is going to be, f star tn at x, the convolution. Did we define tn? Okay, so I'm using that one, so sorry. Change that to that. I do love how it knows exactly where the line is and erases just the line. And here, fn of x is our sum and goes from 0 to n minus 1, I believe. Yes. dn of x with a 1 over n. All right, so let's actually evaluate this integral. So it's the sum, sorry, it's the integral from -1/2 to 1/2, f of t, and then we will have 1 over n the sum n goes from 0 to n minus 1 dn of x minus t. So what's the first thing we should do?
How can this be true? Because you for f of x.
No, Tn of x doesn't approach 0. Tn is the Fourier series approximation for f. So Tn of x is the Fourier approximation to f. Right. Well, here's the thing. Fn is the sum. So Tn f of x is the sum, and goes from minus, I think n minus 1 to n minus 1 of 1 minus absolute value of n over n f hat of n e to the 2 pi I n x. So this is going to be the nth Fourier approximation. So the difference between this and what's the difference between this and the standard Fourier series approximation? The 1 minus absolute value of n over n. It's a weighted Fourier sum. So by putting in these extra weights, things are going to converge much better. No, the Fourier kernels are the approximation to the identity. Using the Fourier kernels, we then build up a approximation to the function. So Tn is going to be the approximation to the function. It's the Fn's that are the approximation to the identity. And so what we're going to do is we're going to integrate f against one of these Fourier kernels. So we're going to look at the integral of f of t times Fn of x minus 2. All right, well, let's do this integral. So there was a suggestion to switch the sum in the integral. So it's 1 over n. The sum n goes from 0 to n minus 1. Integral from minus a half to a half f of t. And then what is dn of x minus t? If we look at what's going on in terms of the Fourier kernel, there's lots of different ways of doing this. Dn, I can write as the sum of, n goes from negative n to n, or I could just use this more useful expression over here, that the Fourier kernel is just this sum of 1 minus absolute value of n over n, and then the two different exponentials. That's going to make the calculation a little bit easier. I could go through and do it like this. But you would see that if I wanted to go through at this point, I would then have to have a sum over here for the dn, right? Sum for dn. And this is getting to be a mess now. I'm going to now have a double sum with an integral. So one of the points of this lecture is to talk about what's the best way to do the algebra, right? This is becoming an algebra nightmare. Again, it's fine to start doing the calculation like this, but as we see what's going on, if I want to start working with it like this, it's just not a good idea. So let's revisit and say, well, look, we showed that the Fourier series has this nice expansion. So let's put that back over here. And let's go back to looking at f star fn of x, which is the integral from minus a half to a half of f of t fn of x minus t dt. So this is going to be the integral from minus a half to a half f of t, and then it'll be the sum, n goes from 0 to n minus 1 of 1 minus the absolute value of n over n e to the negative n of x minus t plus e to the n x minus t dt. Why am I only having the sum go up to n minus 1 and not go all the way up to n? Yeah, the big N, the absolute value of n, of little n over big N is just 1, so the subtraction just becomes 0. So I could go up to big N if I wanted to, but there's really no point. I know it's going to vanish there. And so now, if I look at what I have, this is the sum, n goes from 0 to n minus 1, 1 minus absolute value of n over n, integral from minus a half to a half, f of t. And now I have e to the negative n x minus t and e to the n x minus t. So remember, en of x is e to the 2 pi I n x. What is en of x minus t? It's e to the 2 pi I n x minus t. Yes. Yes. Okay, yes, you're right. We did double count E0. So let's make this 1. And then what would we get for E0? We would just get the integral of f of t. So we'll have plus the integral from minus 1/2 to 1/2. So when you look at what is en of x minus t, it's e to the 2 pi I n x minus t. So I can write this as e to the 2 pi I negative n x minus t plus e to the 2 pi I n x minus t dt. And the integral from minus a half to half of f of t is just f hat of 0. When we look at what's going on now, this is just a sum, n goes from 0, so n goes from 1. It goes from 1 to n minus 1, 1 minus absolute value of n over n. Then we have the integral from minus 1/2 to 1/2, f of t, e to the 2 pi I, we're going to have negative n, negative t. So I'm going to write it as negative n of t times e to the 2 pi I negative n x dt plus the integral from minus 1/2 to 1/2 f of t e to the 2 pi I n x to the first one we'll do with a negative t, so we'll do negative t and then e to the 2 pi I n x dt plus f hat of 0. So it's f hat of 0 plus a sum, and goes from 1 to n minus 1. Let's look at what we have. For the first term, we have f of t e to the negative 2 pi I negative n t. What is that first integral equal? The e to the 2 pi I negative n x just comes out of the integral because that doesn't depend on t. What is that first integral equal? So it's the Fourier coefficient, not at n, almost, at negative n, times e to the negative n of x, plus the Fourier coefficient at n times e to the n of x. And from that, we get that this is basically the sum. N goes from 0 to n minus 1, 1 minus absolute value of n over n. let me erase the sum. Interesting. Okay. So what we're doing here is by doing the calculation like this, we see that when we look at f star with f hat of n, this is just going to be a weighted Fourier sum. We just have to be careful in terms of how we write things because of 0. So f star fn at x is basically the sum of 1 minus absolute value of n over n f hat of n e to the 2 pi I n x. And I think if I read it like this, negative n to n, I'm okay. Because now I'm not double counting the n equals 0. So this shows you one of the reasons why we like working with Fourier series. If we look at f convolved with the Fourier kernel, we get the weighted Fourier series. What would you conjecture, without even doing the calculation, f convolved with the Dirichlet kernel would be? Without doing the calculation, what would you just conjecture that would be? It would just, there would be no weights. It would just be the unweighted sum. And so this is just a direct calculation. And we're really using some nice properties of the exponential. The exponential of a difference, is the product of the exponentials. Is that allowed us to split things up nicely? And so the convolution is going to give us this weighted Fourier series or this unweighted Fourier series, depending on which we work with. So if we want to study the original Fourier series, we would much rather take the convolution with the Dirichlet kernel. The problem is the Dirichlet kernel doesn't have as good convergence properties. What happens? Well, as the absolute value of n gets closer to big N, these factors go to 0. And so it lessens the impact from deeper down. Okay. So now we know that f star fn is going to be the weighted Fourier series. What we want to do is we want to show now, claim as n goes to infinity, f star fn converges to f. And that's what we need to prove. The proof actually doesn't use the fact that we have, I believe, this Fourier series, this weighted Fourier series. It's actually a more general proof that if you happen to have a approximation to the identity, and you look at a convolution like this, that's going to uniformly converge to the function. So it's a general convergence result. We'll apply it in the case of Fourier's theorem. So is it a big deal that we have these weights? No. But for a lot of problems, we don't want to have the weights. We want to look at the unweighted sums. So frequently in number theory, what you do is you first study a weighted quantity, which is easier to investigate. So if you've done any work on, I don't know, principal nucleons, you might have a Peterson formula, and you might have the Peterson weights. And then depending on which paper you're reading, people might do a lot of work to remove those weights and look at the unweighted objects. It can be done. Same thing here, so long as your function has sufficient smoothness. So we want to study f star fn of x minus f of x. So we want to figure out how to study this. Well, we know f star fn of x is just f of x times fn. It was just f of t fn of x minus t dt, integral from -1/2 to 1/2. And now we want to subtract off f of x. Does anybody know how to write f of x as an integral? So you could write it as the integral of its derivative. let me change things a little bit and see if this is a bit better. Do you agree that this is the same as the integral from -1/2 to 1/2 of f of x minus t fn of t dt? But I'm just changing variables in the convolution. That a star b is the same as b star a. What would be the easiest function f that I could give you that you could study? I'm not going to give you the zero function. Constant. Which constant? 1. So if I take f of x to be 1 identically, what's this integral equal to? The integral of fn of t is just, it's just 1. Anybody see what I should do now?
You can multiply f(x) times the integral of f of t.
Where 1 equals the integral from -1/2 to 1/2 of fn of t dt. So again, while I like the result, I really want to take the time and emphasize the path to it. I am deliberately trying to show you a lot of bad algebra because it's too easy in a book to just go through the natural logical path that they take after they've seen all the failures. It's worth stopping and trying to think, why did we go this way? Well, if we try to actually use the Dirichlet expansion, oh, good Lord, now we've got a double sum and an integral. It was much better to look for it this way. If I read it like this, I now have minus f of x fn of fn of t dt, integral from -1/2 to 1/2. So this is just the integral from -1/2 to 1/2 of f of x minus t minus f of x times fn of t dt. So this is the integral we need to study. The one in red?
Like, you are,
Right.
you could put t kind of-
Right, right, and that's the brilliance here. And this is why I want to write my convolution not as f of t, x minus t times fn of t. I want to write it as, I'm sorry, I want to write it as f of t fn of x minus t. I want to write it as f of x minus t fn of t. Because now this is going to be really, really nice. So I just need to show that this integral goes to 0. So we must show the integral from -1/2 to 1/2 of f of x minus t minus f of x fn of t dt goes to 0 as n goes to infinity. Okay, well, if we look at this, have I used so far any properties related to Fourier series about fn? All I'm using is that it's an approximation to the identity. You then apply it in the case where it is, the Fejer kernel. But as long as I have an approximation to the identity, this will work. So if we think about what's going on, little f is continuous and periodic, and most of the mass of fn is near t equals 0. So if f is continuous and periodic, f is bounded. F is bounded. Say the absolute value of f is less than or equal to b. So given epsilon, find n1 such that for all n greater than n1, the integral, let's just do absolute value of x greater than delta of fn of t dt is less than epsilon. I'm not going to bother making all the epsilons come out nice. Can I do this? So I'm fixing a delta, and I'm just saying if I choose n to be sufficiently large, then the area under Fn of t is negligibly small. Absolute value of t greater than this. This is what we're getting with respect to t here. So why is this true? Yes, true as Fn is an approximation to the identity. But note, n1 depends on delta. Okay, so if you give me a delta, I can clearly choose an n1 so large that the probability, the area under the curve beyond delta from the origin is as small as I want. Okay. What about f of x minus t minus f of x? How large could that be? What's the largest f of x minus t minus f of x could be? We're having trouble. Shakespeare could help. 2b, right? The worst case would be is one of them is b and the other one is negative b. So we know that the difference in the functions is at most 2b. When do we expect the difference of the functions to be small? So what value? So, yes. So when t is small, f of x minus t minus f of x should be small, right? So given epsilon greater than 0, there exists a delta such that if the absolute value of t is less than delta, then f of x minus t minus f of x is less than epsilon. Why is that true? Sorry, it's not bounded. I need a little bit more than bounded. Continuous, more than just continuity. Nope. It's more than just continuity. Uniform continuity. So here the delta doesn't depend on x. There's just some delta. This is what it means for a function to be uniformly continuous. As long as 2 points are within a given tolerance, their values will be, within a given distance. So what this means now is that if I look at the integral over the absolute value of t less than delta of f of x minus t minus f of x Fn of t dt in absolute value, that's going to be less than or equal to the integral t less than delta of epsilon times Fn of t. And how large can that integral be? It's the most, it's the most epsilon. Because the integral of Fn is 1. And so if I only restrict myself to t less than delta, I can't make the integral larger than 1 because it's a non-negative function. So what we've just shown is that we can find, given any delta, given any epsilon, we can find a delta such that the integral over t less than delta of this is at most epsilon. Oh, wait a minute, if we can make that at most epsilon, then we just use that delta and choose the n1. And then the resulting thing will be at most 2 epsilon. So get at most 2 epsilon for the integral. So how many of you have ever seen a 2 epsilon proof instead of a 3 epsilon? So really the reason that this is a 2 epsilon proof is I was a little bit lazy in terms of just how many steps I want to do. I did the absolute value of t is less than delta. And then in the other cases, they often do the 2 different sides. You go from delta to 1/2, and then you go from negative delta to negative 1/2. And for each one of those, you get an epsilon, you get 3 epsilon at the end. Instead of doing that, I just did it this way. We are not using any properties related to Fourier coefficients, Fourier transforms, anything like that. This is a general statement about approximations to the identity. So even though I'm stating it over here that, there exists, an n such that this is true, where this is coming from the Fejer series and the Fejer kernel, this is true for any approximation to the identity. Yes. Well, it's continuous and periodic on a closed interval. So if you're continuous on a closed interval, you're uniformly continuous. So this is one of our results from real analysis, that a continuous function on a compact interval is uniformly continuous. And we talked a little bit about stuff like this when we did the Riemann mapping theorem. It does get them back on the board, but it's nice to review this and see these results a couple of different times. So there's a lot of consequences we can get from this theorem. So the first is we say a trigonometric polynomial is a finite linear combination of the functions en of x. So it's a finite combinations of sines and cosines. So the first is from Fejer's theorem, we immediately deduce the Weierstrass approximation theorem. Any continuous function can be uniformly approximated by trigonometric polynomials. Well, this is not what Weierstrass really proved. What Weierstrass really proved, in practice was before Fejer, was that if f is continuous, then given an epsilon, we can find some polynomial such that we can approximate it well by this polynomial. And so it's actually immediate. If you just look at the Taylor series of sines and cosines and truncate them and keep track of what is the error. So it's a nice exercise, show that if you know Fejer's theorem, that you can approximate with trig polynomials, then you can take that and then you can deal with the fact that, well, if I want a finite polynomial, I can't have infinite. Well, okay, I only have finitely many polynomials that I have to work with. How much is my error if I truncate them? And then the question is, do you want to assume continuous or do you want to assume continuous and periodic? We did use periodic. Yes. Uniformly just means you can give me one epsilon that works for all x simultaneously. I don't have to keep telling you, okay, if you want this epsilon, this n works no matter which x you take. I want to be within 1/1,000,000. As long as n is at least 10,000, you'll be fine. You don't want the n to depend on the point that you're looking at. Strange things can happen in those situations. Okay, so I'm not going to go through the proof of what happens with Dirichlet. For Dirichlet, they add an additional condition. They add that the function is differentiable at the point x0. And if it's differentiable at the point x0, then you can prove that the original Fourier series converges at the point to the function. The proof is very similar to what we just did. It has to be tweaked a little bit because we do not have an approximation to the identity. And it turns out one of the key ingredients is the Riemann-Lebesgue dilemma, that the nth coefficient has to be tending to 0. And that's going to play the role. But essentially, because f is differentiable, when you look at the Dirichlet kernel, let me punch this up again. It was on this page. When we look at the Dirichlet kernel, the problem, of course, is the denominator can blow up. So if I look at this convolution going on, if I have f of we're doing x minus x, right? F of x minus f of x naught. If I have something like this, I'm worried about multiplying this by something over sine of pi x. As x goes to 0, this could become problematic, right? It could blow up. But if my function is differentiable, if I have f of x, let's say x, let's just choose x not equals 0 to make life easy. If I have f of x minus f of 0 over x minus 0 times x minus 0 times sine of pi x, is this ratio going to be okay? if my function is differentiable? Yes, because if my function is differentiable, f of x minus f of 0 over x is just going to look like f prime. And so by multiplying by 1 in a clever way, I now have x over sine pi of x. Well, x over sine pi of x is fine. That's approximately 1. And then I'm going to multiply this by the sine of 2n plus 1 pi x. That looks like a very large Fourier coefficient. So it looks like I'm taking a very large Fourier coefficient of a quantity like this, which goes to 0. This is the high-level idea of what's going on in the proof of Dirichlet. That by assuming differentiability, I can handle the sine of pi x in the denominator. If you look at the Dirichlet kernel, it does not look like this is something that's going to be really small most of the time, right? So you have a large sum. It's not at all clear that this is going to be small. Whereas for the Fejer kernel, it was clear that as we go a little bit away from the origin, it's really small. It doesn't really matter. I'm not going to go through this. This is just a nice slide on applications. It's in the notes. Once we know that we have point-wise convergence, you can actually use this to evaluate a lot of key sums. So for example, if we happen to know that the Fourier series converges to the function at a point, if we choose, for instance, a really good value, we can then sum the Fourier coefficient. And if we know the function, we now know the sum. So for example, we can use this to actually calculate 1 over 2n plus 1 squared by looking at the function 1/2 minus absolute value of x. If we know the sum of 1 over odd squares, do we know the sum of everything? We went from the sum of everything to the sum of the odds. Well, the sum of everything is just the sum of the evens plus the sum of the odds. The sum of the evens is just 1/4 of the original sum. So subtract that, 3/4 of the original sum should be the odds, something like that. So if we actually know the sum over the odds, we can use this to easily deduce the value of 1 over n squared. So this is another way to actually prove the famous Basel problem. What is the sum of 1 over n squared? You can get this by looking at Fourier series and noting convergence. All right, so let's just define the Fourier transform now. So the Fourier transform is defined as the integral of f of x e to the negative 2 pi I xy dx. I like the negative sign. I like the 2 pi. I can accommodate people who don't want to have the negative sign up there. I don't love it, but I can deal with it. I really want the 2 pi there. So the Schwartz space is the space of all infinitely differentiable functions whose derivatives are rapidly decaying. What does this mean? It means if I take any number of derivatives of f and I multiply by any polynomials, then that is going to tend to 0. Well, technically I've written it's bounded, but I could always then take a higher polynomial to then show that it has to have decay. Why am I doing the absolute value of x plus 1? Well, this way, if I take x going towards 0, it's still going to be okay, and I'm not going to be multiplying by 0. So for instance, if my function vanished, if my function was blowing up at the origin, but I'm multiplying by a huge power of 0 at 0, I don't want that to really cause me trouble. Can somebody give me a good example of a function to think about that would be Schwartz? Yes. E to the minus x. The problem is e to the minus x blows up as x goes to infinity from the negative side. So tweak it a little bit, e to the negative. Yeah, so Gaussians. E to the negative x squared would be a great example. So these are functions that decay very rapidly. And if you multiply them by any polynomial, it still decays. If you take any number of derivatives of them, it still decays. As you differentiate this, you start getting powers of x squared coming down. So polynomials in x coming down. But the e to the minus x squared is still going to grow, is still going to decay so rapidly that this won't matter. And so the big result is the Poisson summation formula. And so we've talked about this a little bit before. The technical condition I need is I need my function to decay like x to the minus a for some a greater than 1. Right? And so I'm going to write it as a is like 1 plus beta. And the reason is the function 1 over x, if I try to integrate the function 1 over x, or I try to sum the function 1 over n, it's infinite. But if I do 1 over n squared or integrate 1 over x squared, that's finite. I don't have to go all the way up to the square. I just need an exponent slightly larger than 1. So if I just go up to x to the negative 1 plus eta, for any eta greater than 0, I will have decay. And so the Poisson summation formula says, assume that f is twice continuously differentiable and that f prime, and f double prime decay at least this rapidly, then the sum of f at the integers is the same as the sum of f hat over the integers. And this was the key ingredient we needed in proving the formula for the theta or the omega function to prove the functional equation of the Riemann zeta function. So this is actually related to an example that I gave in class a few days ago. Here is a function which is integrable, I believe, but blows up at some points. Okay, maybe this is not, maybe this one is not integrable the way I have to find it. This function is definitely continuous, but if I try to look at f of x, it will be the sum and goes from minus infinity to infinity of f of x plus n. See, this is a great function to look at because this big F is going to be continuous. Oh, not going to be continuous, it's going to be periodic. If I replace x with x plus 1, that plus 1 can just be absorbed by all the n's. And the idea is we've just proven some wonderful results about Fourier series and functions on the interval 0, 1. If I give you a function on all of R, well, I can't use those results. So what we do is we take our function on all of R and we basically fold it amongst itself. So we just keep wrapping it around like a clock. You go from 0 to 1, and then once you break 1, you then start back at 0 and you add that mass again, and then you add that mass again. And this gives us a nice wrapped around function. And so when I look at something like this, the hope is that this sum will converge, that I can actually study this function. If my function little f has decay, sure, this function will then be well defined. If my function decay is like x to the negative 1 plus eta, it's going to have enough decay, everything will be fine. But if I take a function like this is a nice continuous function, it's going to be a bunch of triangles. The triangles are going to get higher and higher and higher with smaller and smaller bases. The way I've done things, it will actually have, I think, infinite area. You can adjust it so it doesn't have infinite area. It doesn't really make much of a difference. But if I take x equals 0, then it becomes undefined. And this is similar to the example we had before. So unfortunately, it's not enough to just do the analysis. We have to make sure that things exist first. So I will finish this up in the next class, which will be the last one on stuff like this. We are proving everything under the assumptions that f is twice differentiable. I want to use Dirichlet's theorem as a nice exercise. You could probably prove Poisson summation by assuming a lot less and using Fejers's theorem and having the weighted sums and then take the limit and show that the weights vanish. So it's a really good extra credit problem, a really good exercise. I encourage you to try to do that after we finish the proof. All right.